Alright, hello class. In this video we're going to continue our discussion of section 3.2 and start talking about closed sets. So closed sets, it's a little more difficult to get to our definition. So there's a couple things we need to get to first. So there are a couple concepts we need to establish to begin with. So the first thing is what is called a limit point. Okay, so we say a point X is a limit point of a set A if every epsilon neighborhood V sub epsilon around X intersects the set, I'll say intersects A at some point other than X. Okay, so what is this actually saying? So essentially a limit point, so let's try and break this down. It's X is a limit point of a set if every epsilon neighborhood around it intersects A at some point other than X. This is often sometimes referred to as accumulation points. When I was learning analysis for the first time, we called them accumulation points. They're also thought of sometimes as cluster points. Now I kind of like that name, cluster points. It kind of does give you a visualization of what's happening. But to give you an example of what I'm talking about when we're talking about a limit point or a cluster point, so say we're sitting on this number line here, and our set, let's say, is some A to B. Okay. Now let's say X is here. What we mean by every epsilon neighborhood intersects A at some point other than X means that for every epsilon neighborhood I make, there's another element in this V epsilon in the set as well, so other than X. So it's not just X. Okay, so maybe this is one of our epsilons and this is another one. For these we can actually pick the point right at epsilon, but we don't have to. Here's another epsilon neighborhood. We can choose an element, and you can even go way outside, right, with a large epsilon, because you can just pick whatever point you want. But typically what we want to do is get smaller. So what this is saying is that, in other words, as epsilon gets really small, okay, we can continue to find elements in the intersection between the epsilon neighborhood around X and our set A that aren't also X. Okay, so if we were to zoom in here, and do that down here, So here's our x. And we can get even smaller. So let's say the pink is here. I can get even smaller epsilons and still always find an element that will be inside or will intersect the set and not be equal to x. So the reason this is often called a accumulation point or a cluster point is because what we're saying is that there are an infinite number of points around this x if it's a limit point. Okay, so the idea is that x is a limit point or an accumulation or a cluster point if there are, well, there's a clustering or an accumulation of other points in the set around it. So if there is an infinite accumulation of points of A around X and as small of an interval around X as we want. And so there's an infinite accumulation of points of A around X, and the interval of accumulation can get as small as we would ever want. Okay, so basically, if you have a closed interval, okay, you can almost think of every point in here as a limit point or an accumulation point or a cluster point. So if you think about A, okay, here's A, here's B. Any epsilon neighborhood around A is going to have another element of the interval in it. And it doesn't matter how small we get, we can accumulate points infinitely around A. Okay, and we can continue to zoom in and do this again and again and again. Okay, now something that would not be an accumulation point or a cluster point or a set that had limit points is consider the set just 0 and 1. Okay, so on a number line, here's 0, here's 1, but this is the only elements of the set, right? Any epsilon neighborhood, well, we can have large epsilon neighborhoods. So if we pick an epsilon very large, we can pick the 1 out if we're looking at around 0. Okay, but basically any epsilon smaller than 1 is not going to give us any other points in the set. So for epsilons less than 1, these epsilon neighborhoods have no other elements of the set. Therefore, right, these epsilon neighbors have no other elements of the set, and therefore 0 is not a cluster point or a limit point. For right now, I think cluster point is the nicer word. I will, in a bit, there's a reason why we call them a limit point, and you might be able to guess why that is. It's because if they're called a limit point, that means they're the limit of some sequence in the set. You can almost kind of see that we can create a sequence that converges. Now, notice, this is important, the limit point, or not the, but a limit point of a set does not have to be in the set. Okay, so for example, if I look at the interval, let's say I is the open set 0 to 1, notice that 1 is going to be a limit point of I, because if you take any epsilon neighborhood around 1, you're going to find elements of the set. As small as you want to get it, you will find things that get closer and closer and closer to 1, but it doesn't matter that you never actually get to 1, right? We can find elements in the set other than 1 for any epsilon. However, an element like -1 is not going to be a limit point, because any epsilon neighborhood, say any epsilon less than 1, won't get you any points in the set. So whereas -1 is not. Even if -1 was in this set, so if we did union -1, -1 would not be a limit point. Okay, so limit points, cluster points, they're essentially points that have a bit of uncountable space in them, if you can think about it. Because if you have a limit point, you maybe not uncountable, but you'll have tons of stuff around. I shouldn't say uncountable, but you'll have tons of stuff around that point still in the set. Okay, to give us another example, consider this set here. Let's say 1 over n with n in the naturals. Okay, so this, of course, is the set that goes 1, 1/2, 1/3, 1/4, 1/5, etc. Okay. Now, I can't say that 1 is a limit point, because if I looked on a number line, so here's, let's say 0, here's 1. So this is the first element of the set. Here's the second one at 1/2. Okay, now I can't say that 1 is a limit point, because any epsilon neighborhood around 1 that is, say, has a distance or a radius less than 1/2 is not going to intersect any other number of the or element of the set. However, the other elements of the set start getting closer and closer and closer to 0. So we can say that 0, whoops, going off the screen there, we can say 0 is a limit point of A, because for all epsilon greater than 0, this epsilon neighborhood, negative epsilon to epsilon, will contain a 1 over n of some kind. This is thanks to the Archimedean property. Okay, because we can always find an n in the naturals such that essentially 1 over n is less than whatever real number we choose. Okay, so that's thanks to the Archimedean property. So 0 would be a limit point of this set, even though we're not talking about a full countable, uncountable spectrum, like a big portion of the real line like we had before. We can still call 0 a limit point or a accumulation point or a cluster point because, well, you can almost see it if you try to graph it, that the points of the set cluster around 0. Okay? Now, if you think about why we would call this a limit point, we'll notice that 1 over n actually converges to 0. So 0 is the limit of a sequence within this set. Okay, so that's going to bring us to our first theorem about this stuff, which is really why we call these limit points and not just cluster points. Now, it's good to have both. Most books that would start with topology at the beginning, or most classes that would start with topology at the beginning, would call these guys accumulation points or cluster points. Since we have our sequences, and we're doing this now, that's why we call these limit points, because now that we have all the properties of sequences that we need, we can use those instead of just using cluster points. All right, so this is theorem 3.2.5 in the book, which says that x is a limit point of a set A if and only if x is equal to the limit of an for some sequence an contained in A, satisfying an does not equal x for all n in the naturals. So in other words, x is a limit point of a set if it's the limit of a sequence from the set. So i.e., x is a limit point of capital A if it's the limit of a sequence from A. Okay? i.e., if there exists a sequence A sub n contained in A with an converging to x, and with the caveat that the sequence A sub n cannot equal x for all n in the naturals. And the reason we have this stipulation, because for any x, or really for any little a in the set A, we could just choose the sequence A over and over and over again and get a sequence that converges to A. Even if A is not a limit point. Or here, I'll just say even if A is not a cluster point. Okay, and this is also related to the fact that when x is a limit point of A, every epsilon neighborhood intersects the set with an element other than x. But if you just ignore this possibility here of having a sequence of just all x's or all a's, what this is saying is that basically x is a limit point if there's a sequence in the set that converges to it, i.e. if it's the limit of a sequence from the set. Okay, so let's go about proving this. And I'm going to clean this up first. Okay, so to prove this, we need to do both directions. This is an if and only if. So we're going to start with this first direction, and we'll let x be a limit point of a set A. Okay? So that means for all epsilon, the epsilon neighborhood around x also intersects a point from A. So if it's true for all epsilon, this means each 1 over n neighborhood, so about x will contain an element from A. Okay, in other words, x minus 1 over n to x plus 1 over n will contain an element from A not equal to x for all n in the naturals. So for each n, choose an that's in this v 1 over n, so the 1 over n neighborhood around x intersected with A, provided an does not equal x. Okay, so what this means, this gives us that x and A sub n are in x minus 1 over n to x plus 1 over n intersect A, and this is going to be true for all n in the naturals. Okay, now if both of these elements are in these sets for all n, this implies that the distance between an and x is less than 1 over n for all n in the naturals. Okay, and it will be less than. All right, so i.e. the distance between an and x is less than 1 over n for all n. And this is it. This gives us that we have that an converges to x. So this is from one of the exercises. So therefore, an converges to x thanks to exercise. It's one we've used before. It's exercise 2.3.10, part D. Okay, we proved that in one of the earlier lectures. Okay, and it's true thanks to exercise 2.3.10 since 1 over n converges to 0. Remember, if we can get the distance between the terms of a sequence and the limit less than some other sequence that converges to 0 for all n, then we get that the an converges to x. So you can almost think of this as a squeeze theorem as well, because this is also trapped between 0. So 0 and 1 over n, this goes to 0, therefore these guys converge together. Okay? All right, so there's the first direction taken care of, that if x is a limit point, then hey, it actually is the limit of a sequence from an. Now we're going to prove the other direction. So what we want for the other direction is to show that that if there exists a sequence in A that converges to x, then x has to be a limit point, i.e. a cluster point of the set. So in this direction, we're going to suppose that there exists a sequence an in A such that an converges to x and an is not equal to x for all n in the naturals. Right? So now we're just supposing that there is a sequence in A where an converges to x and each an is actually not equal to x for all n in the naturals. Right? Now we want to show that x is a limit point, and here, just to reduce the confusion, or a cluster point of A. So we want to show that, and this really shouldn't be that difficult to get. We want to show that every epsilon neighborhood of x intersects A with an element not equal to x. Okay? Oh, well, we want to show that every epsilon neighborhood of x intersects A with an element not equal to x. So we have that an is already converging to x. Every an is in A, and every an is not equal to x. So I'm going to let epsilon be greater than 0. Okay. Then there exists a capital N in the naturals where a sub n is less than, or sorry, a sub n minus x absolute value, so the distance between a sub n and x is strictly less than epsilon, provided little n is greater than or equal to big N. In other words, specifically, a sub capital N minus x absolute value is less than epsilon. And, okay, this implies that, if we move some things around here, this tells us that a sub n minus x is less than, well, it's trapped between negative epsilon and positive epsilon, and this tells us that x minus epsilon is strictly less than a sub capital N, which is less than x plus epsilon, which tells us that a sub capital N is in the open interval x minus epsilon to x plus epsilon, which is, of course, the epsilon neighborhood around x. And a sub n is also in A. Okay, So A sub capital N is in the epsilon neighborhood of X, intersect A, and A sub N is not equal to 0. So since epsilon was arbitrary, okay, we can find an A sub capital N sub epsilon for every epsilon greater than 0, where A sub N sub epsilon is in the epsilon neighborhood around X intersect A, implying that X is a limit point of A. Okay, and that completes the proof. All right, so this theorem is actually really helpful because now it makes it a lot easier to tell when something is a limit point, right? So if we go back to that set we had before, this 1 over n, where n is in the naturals, okay? 0 is a limit point of A, since 1 over n is a sequence in A. 1 over n converges to 0, and 1 over n is strictly greater than 0 for all n in the naturals, right? So it's a much, in my experience, it's much easier to sort of tell when things are limit points when you can show that they're a limit of a sequence, which is exactly why we established this definition to begin with that name. Okay, even though that's not their official definition, even though that's not their official definition, it could be because this theorem was an if and only if. Right, so since this is an if and only if, we could actually use this as our definition, although that's not particularly traditional. Okay, so next up, our next definition is basically what happens if something is not a limit point. So here, and this is an important distinction, a point A in A is an isolated point of A if it is not a limit point of A. Okay, so for example, if we again go back to our 1, 1/2, 1/3, 1/4, 1 over n example. Okay, 1 is an isolated point. Right, because it's not a limit point. However, and this is a big one, it's a big however, 2 is not a limit point of A, but it's not an isolated point either because it's not in A, but is not an isolated point of A. Because it's not in A. Right? You can only be an isolated point of A if you're in A. Hopefully that makes sense. Actually, every element of A in this case, is an isolated point. If you think about y, we talked about 1, but with 1/2, well, as long as we pick an epsilon like less than a sixth, right? If we pick something small, we can isolate it. And here, if we pick something smaller than the distance between 1/3 and 1/4, we can isolate 1/3. And if we pick something smaller than the distance between 1/4 and 1/5, we can isolate this. And here, if we can pick something smaller than the distance between 1 over n and 1 over n plus 1, we can isolate 1 over n. We can isolate all of these elements of A, making every one of them an isolated point. However, 0 is a limit point. Okay? But it's not in the set. All right, so that's a big distinction. Isolated points, we're talking about points within the set that we can isolate. Limit points don't necessarily need to be in the set. So note, and this will be even more obvious when we finally get to the definition of a closed set. So note that limit points do not necessarily live in the set. Okay, and as I said, this will be super obvious once we finally get to defining what a closed set is. All right, and here we go. A set F in the reals is closed if it contains its limit points. Okay, so this is now our official definition of closed. It contains all of its limit points. Now, what I want to mention is if we think about the word closed in other contexts, right? Think about what closed means in algebra. Right? A group is closed under addition if given A and B in the group G, we have that A plus B is in G, right? Now we can also do multiplication. In algebra means that A times B is in G. In linear algebra, you have closures of vector spaces, that kind of thing. What we're talking about now is closed in an analysis sense. So a closed set in analysis means that if a convergent sequence is in F, then its limit is also in F. i.e., given, say, A sub n in capital F, F closed means that if A sub n converges to A, then A is in F. So it's a similar idea. Instead of an algebraic operation, right, we take two elements and we add them and we still are in the set. in analysis, what we're saying is a set is closed if given a sequence in that set. If it converges to A, then its a limit also is in F. I think I said A there, but okay. So we're talking about closed under limits, essentially. Now, if we go back to our previous example that we've been looking at, right, the 1, 1/2, 1/3, we've already talked about all right, and 1/4, and on and on and on. We've already done a lot with this set to prove that it's not closed, right? Every point of A is isolated, and the only limit point of A is 0, which is not in A. So A is not closed. Now, here's what we need to really establish right now. Just because it's closed does not mean it's open. This set is not open either. Okay, so A is also not open. Okay, so just so we're clear, it being not being closed does not mean it's open, right? They're slightly independent. There's a little more to it than that, and we'll get to that eventually. But so A is not closed. However, all right, if we consider the set, so if we let the set F be A union 0, then F would be closed. Right? Possibly not what you would expect. We're used to closed sets being like intervals that look like, 0 to 1. But if we took the set 1, 1/2, 1/3, 1/4, and then just took that and unioned it with 0, the one limit it has, this is now closed. Okay. While we're at it, let's go ahead and prove that what we're used to, like consider A to B, right? Consider that to be, or we want to show that this is closed. So let's show I is closed. Right, and it basically has to do with the squeeze theorem, or the not the squeeze theorem. It's the limit ordering theorem, order limit theorem that we had in chapter 2. So okay, so let's let x sub n be a sequence in I, such that xn converges to x and xn is not equal to x for all n. Now we usually, kind of take that for granted. All right, so then this implies, well, x sub n is in the interval a to b for all n in the naturals. Okay, so this implies that a is less than or equal to x sub n, which is less than or equal to b for all n in the naturals. And this is where we're going to use the order limit theorem. Okay, so by the order limit theorem, the OLT, so that from the book is theorem, let me see, 2, 3, 4. we have that A is less than or equal to X, which is less than or equal to B. It's not exactly a squeeze theorem so much as we can just take the limit of all of this and get that A is less than or equal to X, which is less than or equal to B, which implies that X is in A to B. Now, this was an arbitrary sequence in this interval, and we got that its limit point, or that its limit was in A. Okay, so therefore I contains all of its limit points. So I is closed. Okay, part of where this would fall apart is if we tried the same theorem or the same proof with an open interval. If we tried it here with if xn was in the open version A to B, this would give us that A is strictly less than x sub n, which is strictly less than B, and this would give us that the limit, well, we'd have to get the less than or equal to, because that sequence could converge to one of the endpoints. So this would tell us that the limit is in the closed interval, so it might actually be one of the endpoints, which would not actually be in the interval. So that's why we can't utilize this same argument to prove that the open interval is closed, which is good. We don't want to be able to do that. All right, there's still quite a bit left to talk about when it comes to closed sets. Of course, we had a few definitions to crank through before we could even get there. So in the next video, we'll complete this section, finish talking about closed sets and closures, and then we'll move on to the next section. I'll catch you all in the next one. Cheers.